In this video, I'm going to construct ray diagrams for the different types of lenses and mirrors we've been talking about in class. The first one that I'll start with is the converging lens or double convex lens. You can see on your screen that I've set up the lens and the focal length and the center of curvature, or the radius of curvature. Keep in mind that 2 times that focal length is equal to the center of curvature. And just for a quick opening discussion, recognize that if this circle were to continue, this spherical shape, if that sphere were to continue, the center of that sphere would be right over here at that center of curvature. So that's where those come from, and technically there are 2 of them. Here's another part of that circle, and we can see that the center of that circle is over there on the other side. Okay, so let's get started drawing some rays. There are many rays leaving the object that's over here. I'll label the object O. There are many rays leaving in many different directions here. Either that light is being reflected off of the object or it's being given off the object. But regardless of the scenario, there are 3 principal rays that we're most interested in. There's one that's initially parallel to the principal axis. You can see we've sketched that in. And that's going to refract, obeying Snell's law, here through the focal point. One of the second principal ray is the ray that passes through the focal point on the way to the lens. I've drawn that one in here, and we'll see that that will refract through the lens parallel to the principal axis on that other side. And then finally we have the third ray that passes at the principal axis through the lens at that principal axis, and we'll see that it passes through straight on through to the other side. All right, so there is my ray diagram. You'll see that when the object is here at the center of curvature, that I get my actual image located at the center of curvature as well. So we'll see that here in just a sec. I'm just going to grab some line thickness, make it a solid, and here we go. And then there it is. So that should be right there at the center of curvature. I'm off a little bit because of the dimensions that I've used, but it should show up right there. And I'll label that as the image I. Now I need to classify the image. We can see that it is inverted. We can see that it is a real image. The reason that it's real is because these light rays are actually refracting here through the lens and actually do project an image. If I were to place some sort of an index card or a screen here at position C, the image would actually be located there. And it's actually neither of these. It's not enlarged or reduced. It's the same size as the actual object. You can see that just by kind of eyeballing it, or better yet, you could use the concept of magnification being the image height over the object height, that ratio, or in this case the image distance is the same as the object distance, but we'll be talking about that a bit later. For now, let's focus on the idea that it's the same size and there is no magnification there. Let's go ahead and move on to this next instance. We'll call it case number 2, where the center of curvature is, the object is located between the center of curvature and the focal point. Oops, went a little bit too far. Okay, so again, I'm going to sketch in my principal rays. The very first principal ray that I'll draw, again, is the one that is parallel to the principal axis, that refracts through the focal point. Again, I have one that is kind of the opposite of that, goes through the focal point. I barely catch the edge of the lens there. That refracts parallel to the principal axis. Looks like I'll have to extend this ray that I sketched here, so I'm going to go ahead and stretch that guy out. And then finally, I have the third principal ray coming right down through the middle of the lens, right on through the other side. And now we can see that the image is located on the other side of the center of curvature, and we'll see this time that it's actually larger. So if I make a copy of this here, I'll have to extend it up to the principal axis. Now technically, I'm going to label that as my image. And we'll see that it's just kind of, by visually looking at this, you can see that it's slightly larger than the actual object. We can see that again it's inverted. And so I'm going to go ahead and write these things here. Okay, I've just added these little classifications here. Again, we'll see that it's inverted. We'll see that the image is real, again, for the same reason, because the rays actually do pass that point. If I were to place a screen here, it would project onto the screen, and we'll see that the image is actually enlarged. It's larger than the initial object, which was over here. In our last case, we've got the same lens, except now the object is less than the focal length, so we'll identify where the object is here. This is probably one of the funkier ones. So let's take our time here in sketching the ray diagram. Again, ray that's parallel to the principal axis refracts through the focal point, but in this one you have to see that it's actually related to a different focal point. The focal point on this side, I'm going to draw a line here just to kind of help me out, and we'll see that that refracts up and away like so. So you can see that refracted ray is now moving up and away. Our second one is the one that would have gone through the focal point here on this side. So what I'm going to do is send it in that direction and then just kind of sketch in this guideline. It would have gone through the focal point here on this side. That's going to refract parallel to the principal axis. And then finally we have a ray that passes right through the center of the lens. We can see that these three rays that I've drawn here, and I'll label these refracted rays, 1, 2, and 3, are actually diverging, which is in contrast to what's happened in all these other instances. What that means is the image is going to be virtual, and it's going to be on the same side of the lens as the object. So if your eye is over here, and you're looking at this light, you see it diverging from some point that you perceive behind the lens. And we can go ahead and track where that would be using these kind of virtual lines here that I'll draw. So let's go ahead and see where those bring me. I don't know if that's dark enough. Let me thicken the line a bit. Probably a little too thick, huh? Let's get rid of that and try that. All right. Now we can see that come back here, here, and right up there. So those three rays appear to converge on some spot on the same side of the lens that the object is. And what you'll see is that creates a virtual image. So it's now still upright, but now smaller than the actual object itself. And so it creates some interesting classifications of the image. We'll see that in this case it's upright, unlike all the other ones that we've done that have been inverted. We see that this one is upright. We see that the image is actually virtual in this case. We see that these diverging rays on this side of the lens create the appearance of convergence on this side, but the light rays aren't actually there. Your brain perceives them as basically converging on this one spot. And then finally we can see from the ray tracing that the magnification is less than 1. The image is reduced in size. Okay, so the last thing we're going to do is motor on down here and deal with a diverging lens. This one is a bit funky, but all of the different positions are the same along the principal axis, so we only really need to kind of learn one of these. So let's take a look. In the very first case here, we have a ray that is incident on the lens parallel to the principal axis. It's going to refract in a line that is related to this focal point and not the other, just like we saw in that virtual image above that. So I'm going to leave this here as a construction line, recognizing that the refracted ray is up and away from the principal axis. Now I have a second ray that would have passed through this focal point here. I'm going to go ahead and show that again with a construction line, seeing that would have passed here through that focal point. And that ray refracts parallel to the principal axis. And then lastly, I have the ray that passes right through the center of the lens at the principal axis. we can now see that these rays are diverging. And just like we saw in the case above, these three rays, 1, 2, and 3, are perceived by some viewer, some vantage point on the right side of the lens, to have originated behind the lens, on the same side that the object is. So let's go ahead and track that. I will again attempt to draw these lines behind there. I'm going to track this guy back, this one, and then finally ray number 3. And we see then that those rays intersect on the same side of the lens, creating another virtual image. The rays aren't actually there, and I'll go ahead and label this is my image, being careful here that that is my object. We can see now that the image for this diverging lens or double concave lens is upright. We can see that the image is virtual, and we can see that it is again reduced in size. And all of these classification characteristics are true wherever the object is. There's a nice little tool here, an online tool that you can find that models what we've just done. We're starting with the converging lens. You can see that if I move the location of the object, the location of the image kind of dynamically responds to that. So here it is at the center of curvature. We can see that the size of the image is in the same size as the object. It is inverted. As I come now between C and F, we get some magnification. We still have inversion. We see that it's much larger but still inverted below the principal axis. And no image is formed, by the way, at the focal length. Those lines are parallel. They never converge on either side. But now, all of a sudden, we get that virtual image here where we get the image being located on the same side of the lens as the object. It's virtual. Those green lines represent the lines that are perceived by a viewer on the other side. If I come back out here and flip this thing around and make it now a diverging lens, we can see that regardless of where I place the object, I get the same scenario. In this case, I don't get the absence of an image formed at the focal length. I still get an image formed here, but it's always smaller. In this next segment of constructing ray diagrams, we'll take a look at mirrors. We'll start with concave mirror. And again, you'll use some of the skills that you've developed. I've made this sketch here. I've got another principal axis, focal point. Again, the focal point is related to the center of curvature. It's half the center of curvature. If I were to extend this mirrored surface here like so, it would have a center over here. So this is the center of a circle or a sphere if it were three-dimensional. Okay, let's go ahead and start again with our principal rays. We've got a ray that is incident on the mirror. It's simply obeying the law of reflection, and it's now reflecting through the focal point here. Again, one that passes through the focal point on the way to the mirror. Reflects parallel to the principal axis. And finally, I have a ray that strikes the mirror at the principal axis, reflects below the principal axis at the same angle, and produces an image below the principal axis. We can see that here, let's go ahead and grab this guy. And so I'm going to go ahead and draw my image in. Now, it's pretty close. It's not perfect, again, because my alignment's a little bit off, but this image should be located right underneath the object. There's the image. The object is here. They should be located at the exact same position at the principal axis. However, the image is now inverted. We can see that it's definitely inverted here. We can see that the image is real. Again, the image is real because those light rays actually do pass through that point. If we were to place a screen or a card here, we would get that image projected onto the screen, and it's neither of these. It's the same size as the object. One point of interest here, if I were to take a look at any one of these points, let's take a look at this one small interaction here between this incident ray number 1, and we'll call that refracted ray 1 prime. If we were to kind of like blow that up into this kind of, magnification of many orders, we would see that the kind of curvature of that portion of the mirror is really minimized. And nothing fancy is going on here. The physics of the interaction of the light here, I've gone ahead and drawn my normal line in. We would see that that incoming ray that I've called ray number 1 is striking that point, and that point of reflection, reflected ray that comes down, those two angles are the same above and below the normal line here. So I'm going to call that the angle of incidence, theta subscript I, and I'll call the other one theta subscript r, the angle of reflection. And we'll recognize that they are equal to each other. Nothing fancy is going on here. The physics of this is spot on with what you've been doing previously in class. All right, so let's go ahead and move down to some of the other instances. The second one that we'll look at is case number 2. This is where an object is between C and F. We'll draw, again, our principal rays. We'll start with the ray that's parallel to the principal axis, strikes the mirror, and reflects through the focal point. And then I get my next ray that passes through the focal point on the way to the mirror. I just snagged the bottom of the mirror there, and I now reflect parallel to the principal axis. And then our last ray strikes the mirror at the principal axis, reflects right down below the principal axis at the same angle. And again, we see here some convergence. In this case, we again are now, we see kind of some similarities. I don't know what just happened to that guy. There's one. Let's get another one. There it is. All right, so let's draw these guys in there. So there is my image. Let me reset my object because that kind of got askew. I'll label them. Here's my object. Here's my image. And now we classify. Let's recognize that the image is inverted. It is, again, real. And it is enlarged. I have a magnification greater than 1 here. All right, let's go ahead and move on to this next instance. In the next instance, I have the object less than the focal point. Just like with lenses, by the way, for this concave mirror, I don't get an image formed when the object is located at the focal point. So let's go ahead and draw this less than the focal point. I've got a couple of, well, I've got my classic example of the rays that I need to sketch here. I get a ray that is parallel to the principal axis. It's going to reflect through the focal point. I get, this next one is interesting. I get a ray that would have passed through the focal point. Notice that it's just going to skim across the top of that object. So it's at that specific angle, strikes the top of the mirror, that's going to reflect parallel to the principal axis. And then finally, I get my last ray, which strikes the principal axis in the mirror and basically reflects down below the principal axis at the same angle. We can see here that these 3 rays, again, 1, 2, and 3 are not converging, and therefore the image is located now on the opposite side of the mirror. Let's go ahead and sketch it in. So these reflected rays, 1, 2, and 3, appear to originate behind the mirror. I'll go ahead and draw those construction lines in here. And what happens is we see now that the image that's generated is magnified. It's physically larger. The image is bigger than the object. Let's go ahead and classify this thing. Here's my object. Here's my image. It is upright, it is virtual, and it is enlarged. Again, virtual because these orange rays don't actually exist. All right, let's go ahead and move on to our last case. We've just flipped the mirror around now, at least the shape of it. The reflective surface is now on the other side, and we would classify this as a convex mirror. Just like when we were dealing with the diverging lens, it doesn't matter where we place the object, it's going to be the same at all of these different locations. So let's go ahead and draw our principal rays. The very first one is parallel to the principal axis. Notice that I've drawn the focal point over here on the other side. Oops. So I'm going to reflect in relation to this focal point along that line. I'm going to use this as a guideline and then kind of sketch in that reflected ray that goes up and to the left. I have a ray that would have gone through the focal point on this side. Again, I'm going to use another construction line to illustrate that. Would have gone here through the focal point. It's going to reflect parallel to the principal axis. And finally, in my third ray, strikes the mirror at the principal axis, reflects below the principal axis at the same angle. Those three diverging rays, which we'll call 1, 2, and 3, appear to originate behind the mirror. If I track those three lines back behind the mirror, we see that they all intersect and appear to originate at some point here behind the mirror. The nature of our sketch illustrates that the image is upright, it's reduced in size, and it is a virtual image. Again, I'll bring up the Java applet that shows, in this case, the mirror. This is the same one. It allows you to kind of flip between the two. And you'll see here, just by pushing this button, I can change it from a concave lens to a convex one, again, showing the virtual image generated behind the mirror. Great, thanks for watching.